Good evening children. Today we are going to discuss the topic mechanical properties of fluids, and this mechanical properties of fluids is divided into two parts. Now we are going to discuss about the first part. In this first part of this mechanical properties of fluids, first we have to learn about the pressure. Suppose if there is a beaker containing a liquid, now the height of the liquid in the beaker is h, then you can say that pressure exerted by this liquid at the bottom is written as h rho g, where h is the height of this liquid column, rho is the density of the liquid column, and g is the acceleration due to gravity. For example, if this beaker containing the liquid is moving with uniform acceleration moving upwards, then simply g is replaced by g plus a, thereby the pressure becomes h, d is the density here, g plus a is the net acceleration. Similarly, if the beaker containing the liquid is moving downwards with uniform acceleration, then we can write as pressure is equal to h d into g minus a, where g minus a is the net acceleration. So, these are the two cases. First case is the beaker containing the liquid is moving upwards, next case is the beaker containing the liquid is moving downwards. Instead, if the beaker containing the liquid is moving horizontally with some uniform acceleration a, then the surface of the liquid becomes inclined like this. Because of the pseudo force m a acting on the liquid, the surface of the liquid becomes inclined to the horizontal. If theta is the angle of inclination of the liquid with the horizontal, then we can write that this height difference h1 minus h2 by L is the base length, is equal to a by g or a naught by g, whatever a or a naught, that is the acceleration of the liquid, and that can be written as tan theta, this is theta, tan theta is equal to a naught by g. This equation can be used when the beaker containing the liquid is moving in the horizontal direction with uniform acceleration. Next, basing on that particular concept, we here discuss a problem, a simple problem. Here there is a cubical vessel, all the sides are equal, cubical vessel, the side, each side of the vessel is 1 meter. Of course, with a liquid it is kept on the horizontal, and the water or any liquid is completely filled in the beaker. The water is up to the brim of the beaker. Now, this beaker is moving with an acceleration 2 meter per second square in the horizontal direction. Now, the question is how much volume, how much mass of the liquid is expelled or spilling out of the beaker, that is the question. Now, actually if the wall length of the wall is sufficiently long, this liquid might have taken the shape like this. But here, because you are taking the liquid up to the brim or up to the full of the beaker, naturally whatever can be formed, whatever the volume of water or mass of water that can be formed in this region, that will spill out, So, that height of that particular area or particular region we are calculating according to the formula again, tan theta is equal to a by g, a is given as 2, acceleration due to gravity is 10, that is 1 by 5, that is equated to h by L formula. So, from that h or height of this part of the liquid column, we can get it as 0.2 meter. Now, volume of water. Volume of water means in this particular part how much volume is there. It is like a triangle, cross section of that part is a triangle. Therefore, triangle area into height, half into base into height into this particular height, that a triangle into side of the cube already given as 1 meter. So, therefore, we get from this total volume of the liquid that flows, that is the total volume of the liquid that flows out of the vessel that is the total volume of the liquid that is flowing out of the vessel, and from that mass can be calculated. Mass is equal to volume into density. From that we can calculate the mass of water that is spilling out of the beaker because of its acceleration in the horizontal direction. Now coming to the next thing about the density. If I speak about the density, of course every one of you know that density is equal to mass by volume, but here the two cases what we are discussing is these two. In these two, in the first case there are two liquids with masses m1 and m2, densities d1 and d2 are mixed, then what is the density of the mixture? So here the data is given, in the data it was given mass, and therefore in terms of the mass the density of the mixture is equal to m1 plus m2 into d1 d2 by this one. In the same way, if the masses are equal, this is the formula for the density of the mixture. So density of the mixture we are writing in terms of mass and of course the density of the individual liquid. Similarly, in the second case also we are giving the formula for the density of the mixture only, but in terms of volume and densities. Again in the second case, if the volumes are equal, then the density of the mixture becomes like this. So this is how we find the density of the mixture when two liquids are mixed. So the formula is in terms of masses, in terms of volumes. Next. Now we are coming to the case of buoyancy. In the case of buoyancy, simply basically buoyancy means whenever a solid is partly or completely immersed in a liquid, whenever a solid is partly or completely immersed in a liquid, that liquid applies a upward force on the liquid, that is called upthrust or buoyant force or simply buoyancy. So whenever a body is partly or completely immersed in the liquid, we can give this formula: apparent weight is equal to true weight minus upthrust. So apparent weight is equal to true weight minus upthrust. So apparent weight is equal to true weight, that is mg, m volume of the body into density of the body into g minus upthrust. Upthrust is because of the liquid only. So this is the volume of the body and dl is the density of the liquid into g. In this formula, if you take a common v into density of the body into g, if you take common, then we can get 1 minus dl by dv. 1 minute please, I will write it again. I will write it again only once, wait 1 minute. So weight, apparent weight w dash, if you say true weight is equal to volume of the body into density of the body into g, upthrust is equal to volume of the body into density of the liquid into g. If you take v db into g common, I will get 1 minus dl by dv, 1 minus dl by dg. So this is again m mass of the body into g, that is why it is the w we have written, that is the true weight of the body into 1 minus dl by db can be written. So this is the simple formula that we can write when a body is either completely or partly immersed in the liquid. Actually when the body is partly immersed in the liquid, partly immersed in the liquid means, suppose if this is the beaker containing the liquid, if this is the body, that means a part of the body is inside the liquid, a part of the body is outside the liquid, that is called partial immersion. When the body is partially immersed in the liquid, then we can say that weight of the body, is equal to weight of the liquid displaced, that is upthrust only of course. So weight of the body is equal to upthrust. In this upthrust, volume of the body inside the liquid we have to write, because only a part is inside the liquid. So volume of the body inside the liquid into density of the liquid into g, that is equal to the weight of the liquid displaced or upthrust. So rearranging this formula, we can get volume of the body inside the liquid as v into db by dl. And suppose if you write V in by V, that is dB by dl, that we can call it as fraction fraction of the body inside the liquid. Fraction of the, 1 minute please. So, that is the fraction of the body inside the liquid. So, this is a simple formula by which we can get numericals. For example, two bodies are immersed in a single liquid, or a single body is immersed in two different liquids, we can get numericals basing on that. Here there are few points we have to remember. When an ice block is floating on water, when an ice block is floating on water and if ice melts, it is a general conceptual question. For example, there is a beaker containing water. On this there is an ice block. Now the ice block melts. When the ice block melts, what happens to the level of the liquid? Answer is the level of the liquid does not change. In a similar way, the ice block has an air bubble or any cork or a feather or leaf. An ice block may contain air bubble or feather or leaf or cork, any light material. It is floating on the water. Now ice melts, then also the level of water does not change. And one more point you have to remember is ice block containing a lead shot or a stone or any heavy material, then when ice melts the level does not change, the level decreases. So remember, once again I am repeating, an ice block containing an air bubble or feather or cork or leaf, anything light material, if ice melts level does not change. When the ice block contains a lead shot or stone like any heavy material, after ice melts then the level of water decreases. These 2 points you try to remember. Next I gave a simple numerical. Two solids A and B are floating in water. It is observed that A is half immersed and B is 2/3 immersed. What is the ratio of densities of the bodies A and B? Just in the previous slide we showed that V in by V, fraction inside is equal to dB by dl, dB by dl. Now for A, half of the body is floating, therefore this is equated, this was given as half, therefore density of the body number 1 is equal to density of the liquid by 2. In the second case, body B is 2/3 of its volume is immersed. Therefore, this volume in by V dB by dl is 2/3. Therefore, from that we can get density of the second body is equal to 2/3 into density of the liquid. So, this is the density of the first body and this is the density of the second body. If you divide, we get the ratio 3/4, that is the ratio of densities of the two bodies. Next, actually whenever a liquid is flowing, whenever a liquid flows, liquid or gas, actually this chapter is fluids. Fluids means either it may be a liquid or gas. So, we are taking an example of liquid only, but it is applicable for gas also. So, whenever a liquid or gas is flowing, the flow is classified into two types. One is called streamline flow, another is called turbulent flow. So, the streamline flow means it is a regular flow, turbulent flow means irregular flow. So, the streamline flow can at any stage can be converted into turbulent flow. The velocity at which the streamline flow can be converted into turbulent flow, or velocity below which the flow is streamlined, or velocity above which the flow is turbulent, that is called critical velocity. In this critical velocity, R is called Reynolds number, eta is coefficient of viscosity, rho density of the liquid, d remember this is the diameter of the tube, diameter of the pipe through which the liquid is flowing. So, for various values, for example, if the Reynolds number is greater than 3000, the flow is turbulent. If the Reynolds number is less than 2000, correctly speaking it should be around approximately around 500, then the flow is laminar or steady flow or streamline flow. Between 2000 and 3000 the flow is irregular. Irregular in the sense at any stage it can be either converted into streamline or it can be converted into turbulent. So, these are the few points to be remembered regarding the streamline flow and turbulent flow. Next to this is very important, that is Bernoulli's theorem. Bernoulli's principle says that whenever a liquid is flowing through a pipe or any surface, whenever a liquid is flowing through a pipe or on any surface, the three types of energies of the liquid will be constant. What are the three types of liquid? Means potential energy, kinetic energy and pressure energy. There are three kinds of energies: potential energy, kinetic energy, pressure energy. Pressure energy if you say P, potential energy if you say mgh, kinetic energy half mv square, the sum of these three types of energies is constant, This is called Bernoulli's theorem. A part of the Bernoulli's theorem in the sense to explain various numericals or various conditions in the application of Bernoulli's theorem, we go for equation of continuity before going to this. What is equation of continuity? For example, again if a liquid is flowing through a pipe, then the product of AV can be called as volume flux. That is called as volume flux. So, the volume flux of the liquid flowing through a pipe is always constant. Similarly, mass flux AVD, that is called mass flux. So, either volume flux is constant or mass flux can be constant. This is the equation of continuity. Basing on that equation of continuity, we can formulate A1 V1 is equal to A2 V2. As an example, look here, a diagram was given. For example, a liquid is flowing through a pipe of cross section A, velocity V, that is divided into two parts. Here area of cross section A1, here area of cross section A2, here velocity V1, here velocity V2. So, you can write that AV is equal to A1 V1 plus A2 V2. This is a simple application of equation of continuity. Of course, for this will be applied in so many cases while using Bernoulli's theorem. Now, basing on that, we have given one example also. Here the area of cross section 2A, here area of cross section A by 2, here area of cross section A. Similarly, here the velocity 4 meter per second. Here the velocity again 4 and here the velocity they are asking. So, like that we can calculate here AV, here A1 V1, here A2 V2. So, we can write that just now we have written AV is equal to A1 V1 plus A2 V2. We can apply that and we can calculate the velocity of the liquid flowing through the tube N. N means this one, that we can calculate. Now, let us come to exact Bernoulli's theorem. As I told earlier, potential energy, this is pressure energy, potential energy and kinetic energy. Pressure energy, potential energy, kinetic energy, the sum of these three will be constant, or otherwise per unit volume if you calculate P plus rho GH plus half rho V square is constant. Per unit mass if you calculate P by rho plus GH plus half V square is equal to constant. Depending on the data, we can use any of these for three forms. Basing on Bernoulli's theorem, we can have so many applications: aerodynamic lift, or atomizer, or spin motion of a cricket ball. Spin motion of a cricket ball can also be called as Magnus effect, and hydrofoil, of course, that is called as aerodynamic lift. Atomizer means sprayer. So many applications are there for this Bernoulli's theorem. Theoretical applications, please go through. Important theoretical application is, one is called aerodynamic lift, another is called Magnus effect. Spin motion of the cricket ball is called Magnus effect. These two based on Bernoulli's theorem. Next, based on the aerodynamic lift, here I have given a numerical. Go through it carefully. The velocity of air over the upper surface of the wing of an aeroplane is 40 meter per second. On the lower surface it is 30 meter per second. Area of the wing is given as 5 meter per second, 5 meter square, and mass of the wing is 300. Now they are asking net force. Try to understand this word, net force acting on. Actually, in this type there may be two types of questions. Applying the Bernoulli's theorem, P1 plus half rho V1 square, this is on the top or upper side of the wing, and at the lower side of the wing, P2 plus half rho V2 square. Okay, by rearranging we get P1 minus P2 is equal to half into rho into V2 square minus V1 square. So, this is the pressure difference between the upper and lower parts of the aeroplane wing. Now, if you want the force is equal to pressure into area. So, multiply with area. Area means area of the wing. So, we get the force acting. This is called aerodynamic lift. This is called aerodynamic lift. Now, I am telling again, there are two types of questions. With the same data, aerodynamic lift, if they ask, you have to calculate this only. But in this particular question, they are asking net force acting on the wing. So, therefore, we have to add the weight of the aeroplane also. This is the only aerodynamic lift. This is only the aerodynamic lift, and we have to consider the net of two things. One is called aerodynamic lift, another is weight. The resultant of these two is called net force. If they ask only aerodynamic lift, you can stop here only. Then aerodynamic lift, if they ask, do not bother about the mass of the wing, mass of the aeroplane. So, their mass of the aeroplane is not required. So, you must be very careful in doing this type of questions. You have to see whether they are asking aerodynamic lift or uplift or upward force or net force, that we have to calculate. Next thing is velocity of a flux. See, here only it was given Torricelli theorem. Whenever there is a beaker containing a liquid up to a height h, suppose if there is a hole at the bottom, the liquid is coming out of the hole with certain velocity, that velocity is equal to root 2gh. This was given by Torricelli, and that velocity with which the liquid is coming out of the hole is called velocity of a flux. Basing on that velocity of a flux, so many cases are there, one or two cases only we mentioned here. For example, if a liquid is coming out of the hole from here, the velocity with which it is coming is root 2gh. Let the total height of the liquid is capital H, the hole is at a depth small h, then the hole is at a height h minus h. So, this is the depth of the hole and this is the height of the hole. So, remember, try to understand, no confusions at all. In that, height of the hole, depth of the hole, both are given. In the formula for velocity of a flux, we have to have the depth of the hole, not the height of the hole. But while it is coming out, if you want to calculate this horizontal distance travelled by the liquid, then we require this height of the hole. that can be calculated by using kinematics equation. If you remember, a horizontally projected body from the top of a tower, same thing you have to apply, and there we can consider and we can calculate the horizontal distance travelled by the liquid from the hole. 4 into h into h minus s. Sometimes this can be written as 4 h1 h2 under root, where h1 is height of the hole, h2 is the depth of the hole. Anyway, this horizontal distance travelled by the liquid will be maximum when the hole is at h by 2. That means when the hole is exactly at the center, then the maximum distance will be travelled by the liquid. That maximum distance travelled by the liquid will be equal to the height of this liquid. So, these 2-3 points we have to remember. Similarly, when there is a hole made to the, of course, if there is a vessel, liquid is there, if there is a hole at the bottom, liquid is coming out, then the time taken by the liquid to come out, so that the level of this liquid falls from H1 to H2. This is the formula. Again I repeat, what is that formula? When can you use it? When the liquid is coming out of the hole made at the bottom of the vessel, the time taken by the level of the liquid, or height I mean, that is falling from a height H1 to H2, what is the time taken? A is the base area of the vessel and small a is the area of the hole. Like that, that formula is very important for NEET exams. 1 or 2 times they asked numericals basing on this. Next. Similarly, suppose there is a beaker containing a liquid here, here there is a hole and here there is another hole. The liquid is coming out of the hole and falls on the ground, liquid comes out of the other hole is also falling on the ground, but of course at the same height, same distance. The liquid coming out of both the holes is falling on the ground at the same point. That means the range, horizontal distance travelled by the both columns is same. Then if the height of the hole, height of one hole is h, height of the other hole is this. Suppose if the height of this, height means this one, if it is h, the other hole is h minus h. So, go through these formulae. Next to this is called the Newton's formula. Suppose if a liquid is flowing on a surface and the liquid is flowing on a surface, the liquid can be considered as different layers. Suppose velocity of this layer is v, velocity of this layer is v plus dv. The separation between the two layers is dx. Then we can call the change in velocity by distance. Change in velocity of the liquid between the two layers. Again I repeat, suppose if a liquid is flowing on a horizontal surface, consider the liquid as different layers. If v is the velocity of this layer and v plus dv is the velocity of that layer, if the separation between the layers is dx, then dv by dx is called velocity gradient. Anyway, according to Newton, the formula for viscous force between the two layers of the liquid F is equal to minus eta a dv by dx. dv by dx is called velocity gradient, and concern units for coefficient of viscosity we have to go through. Go through these units will be confusing you in the exams. And these are the various factors that influence viscosity, mainly pressure factor and temperature factor. How temperature influences viscosity, how pressure influences viscosity, of course there also for gas, for liquid. So, all these points will be there even in our material, please go through them. Next is Stokes formula. When a body, spherical body is falling from a height, it is falling through a long column of a liquid. When a body is falling through any fluid and it is falling from a long column of the fluid, after travelling certain distance, that body gains a velocity, constant velocity called terminal velocity. the formula for terminal velocity is equal to 2 by 9 r square by eta into rho minus sigma into g. Okay, here r is the radius of the body falling in the liquid and eta is the coefficient of viscosity of the surrounding fluid, rho is the density of the body and sigma is the density of the surrounding medium. This is very important. This is the terminal velocity of a spherical body falling through a long column of liquid. Basing on that, if n droplets combine, this is another important formula, if n droplets combine, the terminal velocity of the combined drop is this. This v is the velocity of each drop, n droplets are combining. Then another formula, if mass of the drop is given, this is another formula in terms of mass of the drop. So, this is a simple problem where 27 droplets are combining, 27 drops, each are falling with velocity v. What is the velocity of the combined drop? As I told earlier, n power 2 by 3, 27 power 2 by 3. So, that is 27 can be written as 3 cube. Therefore, anyway 9v velocity of the bigger drop, combined drop is this. So, like this is the few important points related to fluids part 1, and in the next part we will discuss about the fluids part number 2. In that part we are going to discuss about surface tension. So, I am closing the session for today. Next class we will go for surface tension. Thank you very much.